goes well. Okay, so I'm going to start. Is that right? Should I just start? Can you see my slides?
Yes, we can see.
Okay, thank you very much. Wait a second, let me just, there's something. Okay, now I'm going to start. Okay, thank you very much for the invitation to give the, to present my latest work here. So what I would like to talk about is how to use holography to learn about neutron stars, or more precisely matter in the interior of the star, which we think is strongly coupled. This is work done together with Nicolas Kowensky, who is a postdoc in Sakai in France, and Aaron Poole, who is a postdoc in Korea. And it's based on 3 works, which are given here. The main work about the neutron stars, proceedings where we further compared our results to astrophysical data, and work in progress where I will also show a few very new results which are not yet published. So when I talk about neutron stars, most of you, or not all of you, will be familiar with neutron stars. So what's the theoretical context? When we are talking about the interior of neutron stars, we're talking about dense matter, which is governed by QCD, by the strong interaction. So let me put this talk also in the context of some theoretical questions about QCD, in particular the phase structure. So this I've put up here as a motivational slide about the things we do and don't know about the QCD phase diagram. Probably many of you will have seen this phase diagram in the plane of temperature vertically here and baryon chemical potential mu b. What we need for neutron stars is also to add an axis mu I, which is the isospin chemical potential, because neutron stars are mostly made of neutrons rather than symmetric nuclear matter. So the isospin chemical potential will be non-zero, and neutron stars indicated here will roughly live here, even at higher temperatures nowadays, when we have access to mergers of neutron stars where the temperature is high and which we can detect via gravitational waves. So you see there are many lines with question marks. For example, this line here, which has a question mark, is the deconfinement chiral phase transition, where we have little information at finite baryon chemical potential, because we can't use lattice QCD here. We know that there's nuclear matter at some point and quark matter at asymptotically high densities. In between, there can be more exotic phases, like a so-called quark-ionic phase. I'll briefly get to this also in holographic context in a few slides. In the mu I direction, interestingly, lattice QCD can produce results, because there is not such a so-called sign problem in this direction. So we know that there's pion condensation somewhere here. And you can ask questions: do they coexist with baryons? How does the 3D structure of this whole phase diagram look like? And so on. So these are the theoretical questions that we hope we can contribute with holography. So what I'm going to use is the holographic Witten Sakai-Sugimoto model. I will introduce this in a very brief way, basically just showing you a sketch here. So it's based by works on works by Witten and later Sakai and Sugimoto. One thing I want you to keep in mind already is that it has very few parameters. I get back to this, how I fix them later: the 't Hooft coupling, a scale, the Kaluza-Klein scale, and L. I will get to this in this sketch down here. These are very few, especially compared with other phenomenological models that we have in a neutron star context, where parameters are often 10, 20, or even more. So this is something to keep in mind. It's a top-down approach. It's based on a string theory. It gets somewhat close to QCD because due to this scale that you put in by hand in the geometry, you break conformal symmetry and also supersymmetry. And originally it was applied to spectra of mesons, baryons, glue balls, and so on. And here I'm doing something different. I'm interested in matter, in dense matter. So I'm looking to apply this model for a many-body system, right? So this gives some more complications compared to the single particle spectra done before. So here's this little sketch. That's all I want to say about the model itself. So I've plotted in blue sketches of the background geometry, where the vertical direction is the radial or holographic direction. So up here, you could think of the field theory living. I'm hoping you see my cursor. If not, let me know. And here are two subspaces. One is imaginary time. So this is at a finite temperature. We compactify this direction. So this the radius of this circle depends on temperature. And this.
Actually, I cannot see your cursor. Yeah.
Okay, so I don't know how to fix this quickly, but I'll keep it in mind then if I speak. Okay, I try to not.
Yeah.
Okay. Thanks for letting me know. So in the upper two plots, where I label the directions as tau and x4, the tau is the imaginary time direction, a compact direction in the presence of a finite temperature. X4 is the compact dimension where the radius is given by 1 over mkk, the Kaluza-Klein scale already mentioned. So this is fixed once and for all, whereas the other circle changes with temperature. And you see that there are two geometries which are both solutions to Einstein's equation, and you can compare their free energies, and there's a critical temperature interpreted as a confinement critical temperature where you flip from one to the other. And so up in this plot at the top, I'm in the deconfined background geometry, whereas at the bottom, I'm in the confined geometry. Then additionally, Sakai-Sugimoto added flavor branes to this in order to be able to describe quarks as well, not only the gluonic background. And I always work in the pro-brane approximation, where I don't affect the blue background geometry by the red probe branes. And these are branes and the 8 branes and anti-branes. Interpreted as left and right-handed fermions living on them. And there you see this parameter L comes in, namely the asymptotic separation of these red branes. And the branes can either be connected, that's in the bottom, which is interpreted as spontaneous chiral symmetry breaking, because the SU2 gauge theories, or SUNF in general, gauge theories are not independent anymore on each brane, whereas in the top, you can rotate independently and chiral symmetry is restored. So in this pro-brane approximation, chiral symmetry breaking is locked to the deconfinement phase transition, right? Chiral symmetry is restored if and only I'm in the deconfined geometry. And you might say, if you know a bit about the QCD phase diagram, this is quite a boring or unrealistic version of it. It only holds at large and C at best. But if you want to do realistic predictions for the QCD phase diagram, we have to change this a bit. First of all, I should mention we can include baryons. That will be important later, because when I talk about neutron stars, obviously I want to talk about nuclear matter. In this model, they can be added as instanton solutions on the flavor branes. Of course, if I discuss a dense system with many baryons, I have to resort to some approximations because it's curved space, obviously, and there are many instantons who interact. I can't do the full thing. I'll get later back to what approximations I'm going to use. But before, let me also briefly mention how I get more realistic phase diagrams. I can play around with this parameter L, namely the distance between these flavor branes shown in red. And in that case, basically, if you bring them closer and closer together, there's a new phase coming up, namely the deconfined geometry, but with a broken chiral symmetry in the top left corner of this phase diagram now. And now I can get a chiral phase transition which depends on the chemical potential. Most of what I'm going to do later will be in this deconfined geometry shown here, in the confined geometry shown here. So I'm not going to talk much about chirally restored matters or quark matter. My neutron stars will be made of nuclear matter only. I will ignore the quark matter because I'm working in this original setting of the Sakai-Sugimoto model. But there's one result I want to point out just to show what we can do with the model as a kind of review in this so-called decompactified limit. What we have done a few years ago is we've looked at quark-ionic matter. This is only one slide, again, just to show you what we can do with this model. If you don't know what quark-ionic matter is, it's not important for the following. Very briefly, it's basically nuclear matter at large NC, which has some interesting properties, being in some sense a phase where there are where there's quark-like behavior together with baryon-like behavior. And we found some indications that we can construct this phase. There's a configuration in the Sakai-Sugimoto model where we have this phase with these two features. And I just want you to have a brief look at the phase diagrams at the bottom, done in the chiral limit on the left, where the pion mass is 0, and for large pion mass on the right. And we find that the quark-ionic phase is preferred in a certain region of the phase diagram, in a larger region than is expected maybe, but we shouldn't trust this model for very large mu because it's not asymptotically free. And in any case, that's just an example of what we can do with this model. I'll not get back to quark-ionic matter. Let me show you, explain a few of the technical details that I'm using in this one slide. So I'm working with a D8 brane action. I'm using the Young-Mills approximation. There's also a Chern-Simons term. I'm working with two flavors. So in the bulk, I'm working with U2 gauge fields, which I may separate in abelian and non-abelian components. That's what you see in the first line. I'll work in the confined geometry with maximal separation L. So this L will no longer be a free model parameter for us. So I'm down to 2 model parameters. The new things we did is we added a pion mass, which is non-trivial in this model, in contrast to other models like D3, D7. So we do it in an effective way, basically making the connection to chiral perturbation theory here and adding a mass term to our action. We also allow for a pion condensate. I'm not going to go into the details how we do this technically. We rotate our system in order to have this pion condensate in the boundary conditions. That's based on the paper I'm putting here as a reference. We had to generalize this a little bit because we want to work at finite baryon and isospin chemical potential. Then, as I said, it's too difficult, or it's very difficult to work with instantons themselves in a many baryon system. So what we do is we use a homogeneous ansatz, meaning think of instantons overlapping such that there's no spatial dependence anymore. It's just a homogeneous soup of instantons. So the only dependence is the holographic coordinate, which I call Z here. So the AI, the spatial gauge fields, will depend only on Z. And I'm allowing for these to be anisotropic, which will be interpreted as rho mesocondensation in the extreme anisotropic case. I'll show you in the phase diagram in a second. As I said, I put the boundary conditions here on the right. Because of the rotation we are doing for technical reasons, the pion condensate appears in these boundary conditions. We determine the pion condensate dynamically. That's important. It's just it's not just a number. It depends on mu I and mu B. And in the box at the bottom, you see what then we do practically. We fix the baryon isospin chemical potential. That's all 0 temperature. We solve the classical equation of motion for our gauge fields and minimize the free energy with respect to all of the parameters that are left, some of the boundary conditions, including the pion condensate. And then we compare the free energies by inserting back the solutions into our action and construct a phase diagram. So let me show you this phase diagram first before I get to the neutron stars. So first of all, I should tell you how I fit the parameters. There are only 2, and we do so by reproducing properties of the isospin symmetric onset of baryons, and the pion mass. It turns out the raw meson mass in this fit comes out also very nicely in a physical, assumes its physical value. And once we fitted these parameters, here's our prediction for the phase diagram in the mu b, mu I plane. So this is all calculation now, these lines. I have to go relatively briefly. I want to get to the neutron stars. You see, for example, if you go to high mu b, there's a phase that I term b, that's pure nuclear matter. But you have a transition to pi b, which is a phase where a pion condensate coexists with nuclear matter. This is one of the questions you can ask in a neutron star. Is there pion condensate in the interior of a neutron star? If you go to large mu I, that's interesting. If I want to compare with the lattice calculations, you see there's a pi and a pi rho phase. This is purely mesonic, so the baryons only are switched on after a certain threshold in mu b, as you can see. I want to very briefly mention, obviously there's this strange non-monotonicity in the phase transition line. We checked that it goes away if we increase the 't Hooft coupling, but let me say not much more about this. This is interesting for the following. The blue line now that you can see is the line where neutron stars live. Because in neutron stars, I want matter to be neutral electrically, and I want it to be in better equilibrium. This gives me a relation between the chemical potentials, and neutron stars live on this line. The marker you see is the heaviest neutron star we can create. So the neutron stars you will see later live on this segment, in this lower segment of the blue line up to this marker. And one prediction the model makes is that there's no pion condensate in neutron stars, right? So the blue line does not cross the region with a pion condensate. So I can now restrict myself to pure baryonic matter. All right, so the last 10 minutes or so, I think, which I have, let me use that to get to the main result about neutron stars. So here's a little sketch of what a neutron star is, in case you've never seen this. There's a core and a crust. Roughly speaking, the core is our homogeneous nuclear matter, supplemented by leptons, meaning electrons and muons, to balance the positive charge of the protons. And there's a crust, typically 1 or 2 kilometers thick in a neutron star, whereas the radius of the whole star is typically of the order of 10 kilometers. And the crust, if you wish, is almost like a solid state, as you know it from Earth, at least in terms of the structure. It's made of a crystalline structure where nuclei are immersed in a lepton gas, as you can see in this little sketch here. So in our holographic calculation, these bubbles, these nuclei, will be the nuclear matter constructed from holography. And I do add leptons to our action, to our free energy. In the core, I'm just using our homogeneous nuclear matter from holography. When I construct a mixed phase, I also have to come up with an approximation for the surface effects, right? Because I have bubbles there. I use the so-called Wigner-Seitz approximation and put a parameter for the surface tension for the surface between the nuclear matter and the leptons. So that's a third parameter of our model, which comes from the outside. In principle, I could calculate this. We haven't done this for now. I could calculate this from holography, but here's a parameter. But once I fix all of this, the structure I'm showing there, these bubbles, that's all calculated dynamically. So the size of the bubbles and the density inside, that's all dynamical. And in particular, the crust-core transition is also dynamical because I will compare free energies and check at which radius these phases win energetically. So before we get to the stars themselves, here's the purely holographic results. So in the upper right corner, you see a comparison of the free energies of the certain phases as a function of the neutron chemical potential. On the left of this plot, the vacuum wins. You see the lowest line wins. So I'm in the vacuum. Then I go to the mixed phase, that's the crust, right? The red curve. Here I chose a certain value for the surface tension, 1 MeV over Fermi squared. And at some point, homogeneous nuclear matter wins, and that's the crust-core transition. So at the very right of this plot, it's the core of the star. In the bottom left, I'm showing the proton fraction. That's interesting, especially for people familiar with neutron star physics. You see the color coding is the same as in the upper right. So the red curve is the crust, the mixed phase. I'm starting from almost symmetric nuclear matter, where the proton fraction is just 1/2, right? Same number of neutrons and protons. This goes down. One expects this. It gets more neutron rich. And then at some point, I jump to the black line. That's the crust-core transition. And our model predicts that once I'm in the core, the proton fraction increases a bit. This is all nice and corresponds to what people see in other models. What is an artifact is the huge numbers of the proton fraction. You see, it never gets very low, never far away from 50%. We understand that this is unphysical because of our approximation. Basically, the semi-classical large NC approximation we are using here. We can improve on this. It has been done for single baryons. It's not so easy for many baryon system, but first steps have been done in this reference I'm putting here. But for now, we have to live with this unphysically large symmetry energy, which is the energy I need to go away from symmetric nuclear matter, right? So my matter in the neutron star is almost symmetric, not quite, but almost 50-50 between neutrons and protons. Okay, so now I finally get to the neutron stars themselves, for which, of course, we need our holographic microscopic results to be coupled to actual gravity, right? Because the neutron stars are held together by gravity. We do this by the Tolman-Oppenheimer-Volkoff equation. So the equation of state comes from holography. This is just plugged into the TOV equations, and we calculate a mass and a radius for a given central pressure. And varying the central pressure gives mass radius curves. Before I get to these curves that you see here, have a look at this table where certain fits of my parameters are shown. And you see I can fit to vacuum properties like the pion decay constant F pi, rho meson mass. You get values of top coupling of the order of 10, values of the Kaluza-Klein scale of the order of 1 GeV. The third line is important. It shows what happens if I want to fit against many body properties like the nuclear saturation density N0 and the binding energy. You see I get some deviations, still the same ballpark, but that means, strictly speaking, if I want to fit everything, so to speak, I would have to stop here, but that would be expecting too much from the model. So I should rather say it only has 2 parameters. So I'm quite happy that with parameters of this order, I can approximate properties in the vacuum as well as in the medium quite well. And then let's look at these mass radius curves. So vertical axis is the mass of the star, horizontal axis is the radius. I varied the parameters now in this ballpark just discussed. The gray band is given by astrophysical data. Each curve has to touch or go into this gray band because we know there's at least one star which has 2.1 solar masses. So in this case, the blue, the red, and maybe just about the black curve work. The green can be excluded, right? That's how this logic works. I can look at other properties. At the bottom left, you see the so-called tidal deformability, which people have extracted from the gravitational wave detection of a neutron star merger. The band, again, comes from that data. Now the 4 curves turn out to be all on top of each other, plotted as a function of the compactness C, which is mass over radius. So there's some kind of universality relation between these different equations of state. But more importantly, the dots are the 1.4 solar mass deformabilities, which are relevant, and they all lie in this gray band. So it looks quite good. So it seems we can reproduce the data from astrophysical observations. As a reminder, I've just repeated these plots at the top here, and at the bottom, this is more of a theoretical aspects. Our equations of states, or pressure over energy density, from the 4 cases just discussed in the same colors, are plotted here and compared with a band taken from the reference at the bottom of your screen, which interpolates between perturbative QCD at extremely high densities, upper right corner of the plot, and current effective field theories for nuclear matter at the lower left corner of the plot. And the band in between is obtained by putting together all constraints from astrophysics, from neutron stars, plus some thermodynamic consistency conditions. And we can check how our holographic curves fit into this. You see at very low densities, there's some deviation. Interestingly, our heaviest stars are still within the band, which is a nice consistency check. At very high densities, our curves deviate, but that's again understandable because our model is not asymptotically free, so we don't expect to produce perturbative QCD at asymptotically high densities. Finally, before I conclude, what we've done then is, when you realize you just have 2 parameters compared to 20 in other models that work on neutron stars, you might say, why not explore the whole model parameter space and make robust predictions for all possible parameters. That's what we've done here. So have a look at the upper left, at the left plot. So I'm plotting the tidal deformability against the 't Hooft coupling. So I'm varying the 't Hooft coupling. And the blue band is the band where the Kaluza-Klein scale is chosen such that the heaviest star is exactly 2.1 solar masses. And then I read off the prediction for the tidal deformability, and you see it's within the band, as expected from what I showed you before. If I require my maximum mass star to be 2.5 solar masses, you see I'm getting out of that band. So that gives us a prediction for the upper mass of a neutron star, which we currently don't have from observations. And that's just a nice way of showing how this model can work. Notice that this is now completely parameter independent. For any parameter of the model, I can make this prediction. If the mass gets too large, I can't reproduce at the same time the correct tidal deformabilities. I should say it's a band, not a line, the red and the blue, because I've varied the surface tension parameter a little bit just to check its effect. I should mention, of course, this is the very bottom of this slide, that this is not the only work on applying holography to compact stars. Instead of quoting all the other works, I've quoted here 2 reviews. Maybe just to put it into context, we were the first or the only one so far who introduced the isospin asymmetry, which allowed us to account for neutrality and better equilibrium and for the crust, right? So that's the most important thing. We built the whole star from holography, so to speak. And that's also remarkable because even other models used in neutron star physics usually just patch together different models and then build their star. So I should come to an end. As 2 take-home messages, let me just tell you or repeat that we can use the Witten Sakai-Sugimoto model for a QCD-like theory with basically all the necessary ingredients. We've included an isospin asymmetry into baryonic matter, from which we can study
Andreas, thank you for this interesting
and construct neutron stars. Obviously, there's a lot of improvements that are possible. I'm listing a few of them here. Probably I shouldn't go through all of them because my time is up.
So there is one question. Kazim is asking,
Andreas, thank you for
a neutron star with quark matter in the core.
So there is one question.
Okay,
I'm here. I can.
Yeah. Can the model predict a neutron star with quark matter in the core?
Okay, I understood the question. Yes, so here I've only focused on nuclear matter because I'm working in this in this version of the model, right? So I'm working at 0 temperature. There's only nuclear matter, no chiral phase transition. One can work in this version of the model, and to some extent we've done this here in these phase diagrams where it was very fast. So there is a transition from nuclear matter, that's this green schematic geometry, and there's a transition to quark-ionic matter. If it wasn't for quark-ionic matter, there would be a transition to quark matter, I guess. But the point is, in this model, the problem is that this transition is at extremely high densities. So if I use this model, I guess in all versions that I know of, the transition to quark matter would be at densities beyond neutron star densities. That's different from other approaches like the VQCD model, where they do see a transition in a neutron star, at least potentially. So one would work have to work a bit harder with this model in order to see this transition. But obviously, this would be an interesting thing to do in the future. I think I put it as one item here at the list. The second from the bottom is exactly that question.
Okay, thank you, Andreas. I think there are no more questions. We can start the next. So, Ali Singhzadeh from IPM